Ever tried taking a picture of a hummingbird's wings, in motion? It's a total blur, right? Way too fast. Now imagine trying to capture something even faster. Like, how about electrons zipping around inside atoms? That is the mind-boggling world of attosecond physics, and that's exactly what we're diving into today.
Right. It's wild.
We're going to be talking about capturing events on a timescale so short, it's almost impossible to wrap your head around. We're talking billionths of a billionth of a second.
Yeah. To put that into perspective, 1 attosecond is to a second what 1 second is to the age of the universe. Crazy.
Exactly. It's an incredible feat. And you know what's really groundbreaking? Scientists can now actually generate bursts of light that last for just a few attoseconds.
Exactly.
This is what earned 3 physicists, Anne Lou-Hillier, Pierre Agostini, and Ferenc Krausz, the 2023 Nobel Prize in Physics.
For sure. Their work allows us to freeze those ultra-fast electron movements, essentially giving us the ability to, film the quantum world in action.
Okay, so before we get into how they actually pulled that off, I need a little refresher here. Scientists have been using lasers to study fast processes for a while now, right? What was the limitation with that?
So you're right. Lasers have been essential tools for capturing fast events, right? But with these traditional lasers, researchers hit a wall around the femtosecond range, which is a millionth of a billionth of a second.
Still very fast.
Oh, for sure. It is incredibly fast, but just not fast enough to see electron movement.
So it's like trying to study a cheetah, in a full sprint, but you're using a camera with a super, super slow shutter speed. You'll just end up with this blurry mess.
Exactly. Electrons move unbelievably fast, incredibly fast within atoms and molecules. And trying to observe them with just femtosecond lasers, that would be like trying to capture a hummingbird's wings with a 1-second exposure.
Yeah.
It's just not going to happen. You need a much, much faster shutter speed to freeze that action.
Okay, so how do they make that leap from femtoseconds to attoseconds? How do you even begin to create a burst of light that lasts for only a few billionths of a billionth of a second?
It's really an incredible accomplishment in physics, and it involves harnessing something called high-order harmonics, or overtones, in light waves. You see, just like a musical note can have overtones, those higher frequencies that give it a richer sound, light can also have overtones.
Hold on. Are we really using music to understand the fastest events in the universe?
Kind of.
I kind of love that.
Yeah. It's a surprisingly apt analogy. These high overtones in light have much shorter wavelengths, and it's these incredibly short wavelengths that hold the key to creating attosecond pulses of light.
So let me guess. Someone figured out how to generate these high overtones in a controlled way.
Yeah, so that's where physicist Anne Lou-Hillier comes in. Back in the 1980s and 90s, she made a groundbreaking discovery. She found that by shining a specific type of laser, an infrared laser, through a noble gas like argon or xenon, you could coax the atoms in that gas to emit light with these incredibly short wavelengths.
So she essentially created a system that could generate these high-pitched, super fast light waves.
Right.
That's incredible. But how do we go from those short wavelengths to actual attosecond pulses of light?
That's where the work of Pierre Agostini and Ferenc Krausz comes in. They built upon Lou-Hilier's findings, and in the early 2000s, they managed to actually generate these attosecond pulses. Agostini's team figured out how to create a train of attosecond pulses, while Krauss's team took it a step further and isolated a single attosecond pulse, the shortest burst of light ever created.
Okay, so now we can create flashes of light short enough to freeze the motion of electrons. But how does that actually work? What's happening when those lasers hit the atoms in the gas?
So it's almost counterintuitive, but when these intense laser pulses interact with the gas atoms, they can actually knock electrons free from their orbits.
Wait, so it's like the laser's literally knocking electrons off of their atoms.
Yeah,
I thought lasers were supposed to be precise.
they are, but the energy in these laser pulses is so incredibly focused that they can temporarily overcome the forces holding those electrons to the atom. But here's where it gets really interesting. These electrons don't stay detached forever. The pull of the atom's nucleus is strong, and they're eventually yanked back in.
Okay, so it's like a game of cosmic ping pong with electrons getting batted around.
I like that. But the key takeaway here is that when those electrons are pulled back toward the nucleus, they release this excess energy they absorbed from the laser, and they release it as a burst of ultraviolet light, light with a much shorter wavelength, and therefore higher energy than the original infrared laser light.
Ah, so it's that burst of ultraviolet light generated by the returning electrons that actually gives us the attosecond pulses. It's like the atoms themselves are emitting these incredibly short bursts of light.
Precisely. And it's these attosecond pulses, these incredibly short bursts of ultraviolet light that allow us to film the universe at its most fundamental level.
This is absolutely mind-blowing. So we've essentially figured out how to create flashes of light that are to what a second is to the age of the universe.
Yeah.
But what doors does this really open in the scientific world? What's the big deal about being able to see things on the attosecond timescale? We'll tackle that and more after the break. All right, so we've established that we can now generate these mind-blowingly short bursts of light, these attosecond pulses, but I'm still a bit stuck on the so what. What's the big deal about seeing things on this incredibly fast timescale?
Well, imagine trying to understand how a car engine works, but you can only look at still images of the engine. You wouldn't be able to see like how the pistons move, how the valves are opening and closing, or even how the fuel ignites. You need to see the engine in motion to truly understand how it works, you know?
Okay, that makes sense. So we've basically gone from blurry, still images of the quantum world to high-speed video.
That's a great way to put it. Yeah, attosecond pulses, they allow us to see the dynamics of the universe at its most fundamental level. For the first time, we can directly observe how electrons behave in real time.
And we're talking about events happening in attoseconds, billionths of a billionth of a second. It's like having a camera that can capture a thought mid-flight. But why is being able to see electron movement such a big deal?
Well, because electrons are like the workhorses of the universe, right? I mean, they are involved in almost every aspect of how matter interacts with other matter. For example, they form the bonds that hold atoms together in molecules. They're also the things that carry electrical currents. They're responsible for the colors that we see, the light emitted from stars. Understanding electron behavior is key to understanding how the universe works at its most fundamental level.
So it's not just about seeing faster. It's about seeing the very processes that govern chemistry, physics, even the biology of life itself.
Exactly. And the implications of this are massive. Let's just take a simple example. A chemical reaction. With attosecond pulses, we can actually watch how a chemical bond breaks and forms at the level of individual atoms and electrons. You can actually see how the energy is exchanged during these reactions and how molecules change their shape, all in incredible detail.
Wow, so we're not just talking about understanding chemical reactions on paper anymore. We're talking about watching them unfold before our very eyes in super, super slow motion. That's wild.
Yeah, it really is. And this ability to observe these fundamental processes in real time has the potential to revolutionize countless fields. Let's take electronics, for example. Our smartphones, computers, they all rely on the movement of electrons.
Okay, so how does seeing electrons at this incredibly small scale actually translate into like a better smartphone?
Right, so right now we're reaching the limits of how fast electronics can operate. With attosecond science, we can study how to manipulate electron behavior at these incredibly short timescales, which could lead to the development of entirely new types of electronics that operate thousands or even millions of times faster than anything we have today.
So our future smartphones could be ridiculously fast.
Right.
But what about other fields? I've heard that attosecond science could also have a major impact on medicine.
Absolutely. Imagine being able to use attosecond pulses to take snapshots of biological processes as they happen. We could potentially see how proteins fold, how viruses replicate, even how neurons fire in the brain, all with a level of detail that was previously unimaginable.
It's like upgrading from like a blurry X-ray to a high-definition 3D movie of what's happening inside our bodies.
Precisely. This could revolutionize medical diagnostics, drug discovery, and even lead to completely new ways to treat diseases at the cellular level. Imagine being able to target individual cancer cells with incredible precision, minimizing damage to healthy tissue, or being able to diagnose diseases at a much earlier stage when treatment is much more effective.
It sounds like we're entering a whole new frontier in medicine, but those are just two examples, electronics and medicine. What other doors does attosecond science potentially open?
Oh man, the possibilities are almost endless. Attosecond science could lead to breakthroughs in material science, allowing us to design stronger, lighter, and more durable materials. It could revolutionize energy production, making solar cells more efficient, or even leading to new forms of renewable energy. And it could even pave the way for quantum computing, allowing us to harness the bizarre world of quantum mechanics to create exponentially faster computers.
Wow, so we're not just talking about incremental improvements here. We're talking about like potentially paradigm-shifting breakthroughs in multiple fields.
That's exactly right. Attosecond science is more than just like a new tool. It's a new lens through which to view and understand the universe. It's a testament to human ingenuity, our constant drive to push the boundaries of knowledge and our unquenchable curiosity about the universe and the rules that govern it. What seemed impossible just a generation ago is now reality, and it's impossible to predict what wonders await us as we continue to explore the universe on ever shorter timescales.
This is all incredible. It's like we've opened up this whole new chapter in the book of scientific exploration. But I have to ask, how do scientists actually set up these experiments? It's not like they're sitting there with special attosecond microscopes, right? We'll get into the nitty-gritty of these experiments when we get back.
Yeah.
So we've been talking about like filming the universe at the attosecond level, but what does an attosecond experiment actually look like? It's not like scientists are, peering through microscopes with super fast shutters, right?
You're right. It's not quite that straightforward. Think of it more like using a super fast strobe light in a dark room.
Okay.
Each flash of the strobe freezes the action for a fleeting moment. And by carefully timing those flashes, you can piece together this sequence of events, even if those events are happening incredibly fast.
So it's like using a strobe light to break down a hummingbird's wing beats into individual snapshots.
Exactly. In attosecond experiments, those strobe lights are the attosecond laser pulses. Scientists will use a series of these pulses, timed with incredible precision, to illuminate a sample.
Okay, so instead of a hummingbird, we're talking about something like a molecule undergoing a chemical reaction.
Precisely. Scientists might send an initial attosecond pulse to trigger a specific event, like breaking a chemical bond in a molecule. Then they send another pulse, delayed by a very, very specific amount of time, to probe the state of the electrons after that bond breaks. And by varying that delay time, pulse by pulse, they can build up a sequence of snapshots, essentially creating this flipbook of the electrons' movements.
So it's like those old school flip books, they animate a scene when you flip through them. Except here, we're animating the movements of electrons at a speed that's almost impossible to grasp. That's some seriously next-level science. But it also sounds incredibly complex and expensive. What kind of setup do you need to even attempt this kind of experiment?
While it's true that attosecond science requires highly specialized equipment, the field is becoming more accessible all the time.
Oh, really?
Yeah. Early experiments required, these huge, complex laser systems that filled entire rooms.
Wow.
But advancements in laser technology are making these experiments more compact and less expensive.
So you're telling me that we're getting closer to the point where attosecond science isn't confined to massive national laboratories?
Exactly. There are now tabletop attosecond light sources, which means that more research groups around the world can participate in this, exciting field of study. As these technologies continue to develop and become even more readily available, we can expect to see an explosion of new discoveries.
That's incredibly exciting. It feels like we're on the verge of this whole new era of discovery, a time when scientists can directly observe and understand the universe's inner workings at a level of detail that was unimaginable just a few decades ago.
It's an incredible time to be a scientist. The development of attosecond science is a testament to, human ingenuity, our constant drive to push the boundaries of knowledge, and of course, our unquenchable curiosity about the universe and the rules that govern it. What seemed impossible just a generation ago is now a reality, and it's impossible to predict what wonders await us as we continue to explore the universe on, ever shorter timescales.
It's enough to make your head spin. From trying to capture the blur of a hummingbird's wings to filming the lightning-fast dance of electrons, attosecond science has opened up a whole new realm of possibilities. It's a powerful reminder that the universe is full of mysteries waiting to be unraveled, and the only limit to our understanding is, really, just the scope of our imagination. Who knows what groundbreaking discoveries await us just around the corner? Thanks for joining us on this deep dive into the incredible world of attosecond physics.